For us to understand everything we possibly can about the kinds of rocks that are in the area around the landing zone, what their histories have been, what they're made of, whether there are health impacts from them, what kind of sand or regolith or soil is created from them. It's a really fundamental question. What is our environment?
Hello, I'm Colleen Stover with the Center for Space Policy and Strategy, part of the Aerospace Corporation. Welcome to the Space Policy Show. We're glad to be back. Thank you everybody for joining us. With over 150 episodes spanning over 5+ years, we are one of the longest running space policy podcasts on air today. And of course, the center does do deeper research on topics spanning across the space sector. So you can go to csps.aerospace.org and check those out. Today, we're going to talk about Mars, specifically science on Mars. More specifically, what should the highest priority science being done on Mars look like when humans arrive there? What do we need to learn in order to survive and thrive one day? What can we learn from the moon now? And what is this kind of space science? Why is it even important? How does it fit into our national goals? So we've got two wonderful guests today. Thank you very much for joining us. We've got Dr. Lindy Elkins-Tanton. She's a geologist, a planetary scientist. She's the director of UC Berkeley's Space Sciences Laboratory. She's the leader of NASA's Psyche mission, and she's a member of the Senior Advisory Council here for the center. She is also the committee co-chair of a report put out recently in December 2025 by the National Academy of Sciences called A Science Strategy for the Human Exploration of Mars. And her co-chair on the report is Dr. Dava Newman, also a guest today. She's an aerospace biomedical engineer and inventor at MIT. She is former director or deputy administrator of NASA, and she is currently serving on Aerospace Corporation's Board of Trustees. Thank you guys very much for joining.
Thanks so much for having us.
So I wanted to start off, we're going to just talk about this. First of all, there's been a lot of debate about moon versus Mars. Is it either? Is it both? Is it one, then the other? But both of them are really important in their own right. So can you kind of talk about that? Is it an either or is it a both? What does it look like?
It's definitely a both, from my personal opinion and hopefully professional opinion, and written up in our report as well. And let's start with consistency of purpose for exploration, and thank you for hitting the high point, science-driven exploration, so that we can do the best science anywhere we explore in our solar system and beyond. So moon first, absolutely. If we look at where we've been living and working in low Earth orbit for over 25 years, going 26 years now, it's fantastic. So anyone 26 and younger listening, you're the space generation. Every waking moment of your life, 24/7, we've had astronauts living full-time in space, amazing. And now we're going beyond. So beyond low Earth orbit, we go to deep space, and we're going to the moon, back to the moon. I'm the Apollo professor at MIT. I'm really passionate about getting people back to the moon. We need to buy down those technologies, have those technological investments. Moon's just 3 days away. Then that paves the way for our even larger aspirations to get humans to Mars. And Mars is just full of so much exciting science and the search for life that we're going to talk about.
Yeah, Lindy, what do you think?
Yeah, I think Dava just, said it exactly right. It's not either or, it's both. And very, very different bodies, different things to learn, different accessibilities, and so much inspiration for all of humankind, we hope.
Yeah. And of course, we're going to talk about it a little bit later, but that's kind of how NASA's been thinking about this for a number of years, right? That kind of stepping stone. But
right.
Why? Yeah, go ahead. Sorry.
So this goes way back, and we've had Mars strategies in the past. But when I've had the honor to be NASA Deputy Administrator, we were very explicit about this. For humanity and human exploration for living in low Earth orbit, space station, going to the moon. It is a stepping stone, and then to Mars. So the great thing is that, that's what I mentioned by consistency of purpose. Keep the strategy, keep the focus, keep the vision through decades. Literally, spaceflight's hard, and it takes decades for us to do this work. But if we can keep that vision, then it really is low Earth orbit to the moon to Mars. So that has been consistent for quite a while. But the exciting part is we're on the verge of realizing it now.
Right, and you're laying foundations right now for something that was you just laid out as being step 3, well, maybe even step 3 out of 4 beyond. But yeah, so step 3 being Mars, and you're laying, but you're laying down some things about that now in terms of what we really need to start thinking about. So why is doing this science campaign now important? Why now?
What a luxury and an opportunity to be able to think well ahead about what we should be able to do when we're there. You know, there's going to be this moment when humans first put boots on Mars, when we're really there, which is going to be transformational for all of humankind. And because of the efforts and the planning and the risk and the thrill of the whole thing, we want to make sure that that we leverage that opportunity maximally for all the possible benefit for humankind. And the only way to do that is to really plan ahead and hear the voices across many, many disciplines, understand where we are in our knowledge, and really prepare for that step. And so the beauty of doing this immense amount of work right now and write this report about what are the most important scientific questions we can try to answer when we first get to Mars is that then we have the time to figure out how to really do it right. We have the time to figure out the technologies, to train the people, to prepare, and to maximize our chances of getting answers for all of these questions. The questions about the origin of our planet, our planetary system, about what makes a planet habitable, about whether or not we are alone in the universe, and of course, the science of humans on Mars. What are the scientific questions about humanity on this planet? And so planning ahead is really the only way to maximize, and we have the luxury of doing that right now.
Yeah. You're going to say something, Dava?
Yeah. So just to emphasize Lindy's excitement to think about the priority science objectives, what we should do, and in particular from our report with guidance from a lot of experts and the community, and opened it up, and we listened to so many people to get input to see that can we really have a science-driven strategy for those first 3 missions, first human missions. We've been studying Mars for 50 years, which is really important for people to know about as well. Orbiters, right? First we just go to Mars and we orbit, fantastic. And then we go and we land, and now we have rovers. And so this 50 years, 5 decades of accumulating scientific information really gives us a great start. And now we're gonna, the question is, what's the best science we can do when we have our human missions, building on that, the amazing history of Mars exploration, and bringing our communities together. And is my sister in another life, but getting all the space scientists together with the human exploration folks, that's just really an important part of the study too. We're not in silos. We're crossing all of our disciplines. That's what it takes, right? The vision is science exploration on Mars with humans. And so we have to just get rid of any of those boundaries, if they're perceived or real, any of those science silos or human exploration, and we work together. And that's another, I think, important thing to share, is we're really bringing our communities and our cultures together to get this right.
Yeah, I have to add on to that because it's been so important to what we've done. Even in our steering committee, we had a fantastic steering committee. We had 4 panels of experts, 70 people all working on this. And job one for Dava and me and our steering committee was to bring that group together as a team so that we could all speak the same language, and we would listen with a great deal of respect with each other, and then understand where gaps are in knowledge. We had every discipline there, all the different kinds of sciences, but engineering. And here's Dava, primarily an engineer, and me primarily a scientist. And we had astronauts, retired astronauts. So we had the human experience. These are not groups of people who generally ask the same question or speak the same language. And it was so exciting to see how we could come together as a really communicative community and create that synergy and do so much more than we could do individually. And I felt like it was a microcosm of what we're trying to do as a society in this effort. And that's exactly it. We have to get rid of those boundaries and think about it from a higher view, all of us together.
Yeah, I like that. I think, well, my next question was about why NAS was the right one to be doing this, but you guys have answered this question in terms of them being the ones to really get that kind of cross-disciplinary group together. So I appreciate that.
Exactly.
Now, Lindy, you had talked about, you had mentioned something about giving us time to prepare by doing the kind of planning now. And part of that preparation is our technology isn't quite there yet. So this report makes certain assumptions, right? It's the focus is maximizing science, as you guys have driven home, but it makes certain technological assumptions about getting there. So I wanted to ask you guys to just kind of walk our audience through some of those assumptions that are being made before.
Yeah, let me start out on this, and then I know David will have a lot to say too. This is something we talked about a lot. I guess I would say not assumptions, and let me explain to you why. So we had the enviable task of thinking really big. What are absolutely the most important, and in some cases, the most aspirational scientific questions we need to answer on Mars? The ones that we need the people there working with our agents, our AI, our machine learning, our robots. Well, I'm sure we'll talk more about that too. And specifically, we were asked what we should answer, not how to do it. And so you could imagine that the task of saying, here are the questions we should answer with all the measurements that are needed to answer those questions and all the samples that are needed to make those measurements. And at the same time, explaining how we're going to do all of that, that is much more than a 2-year endeavor by our group. So our group is, what's the science we need to answer? And if we had limited ourselves by thinking about what's the technology we have right at this moment, we would not be able to have written down those very most important science questions, the most aspirational ones. And so it's the job of all the rest of the community people who've been working on this for decades and the people who are continuing to work on it to figure out the how. And so rather than so much assuming that things exist, we are laying it out there as a challenge. Here's the most important work we could do. How can we do it? And as Dava said, the how is still to come. It's based on the incredible work that humans have done in space travel over the last decades and decades of work, but there's more to come. Dava, what would you add to that? I know we've talked about this a lot.
Yeah, and so we don't want to get stuck in today. We're projecting to the future. But we do need to start the investments. So I say a little bit about some of the tech investments just real quickly. We kind of categorize that into to 5 pillars. And so here's just a bit of a list. Warm us up. Some of the technologies that we need to invest today for the coming decades, or we won't be ready. We envision this as a couple decades away, maybe 15 years, I hope, fingers crossed. But anyhow, the technology is a little bit communications, observation, right? We don't have those systems at Mars today. Power infrastructure, just infrastructure. We're going to talk about the campaigns, but just with drilling. Guess what? We're going to Mars to search for life. We really need a big push in drilling technology. We can expand it. Lindy mentioned human robot AI teaming. Right? It's not just humans. It's not humans versus robots. It's the suite. We're all explorers. So we're gonna have rovers and robots and humans and hopefully a lot of smart systems that are gonna help us do our best science. We're gonna be there for long durations. We can talk about the campaigns coming up. That's so exciting, being not just on another planet, Mars, but staying there for these long durations. We have to study the astronauts. How are the astronauts performing and keeping them healthy and well and alive? And we envision all the science we talk about next, but we need a huge science laboratory too on Mars. So that's just a sampling of some of the technologies that we talked about and we wrote in the report, and look forward to people reading it and talking to you more about it.
Yeah, no, thank you. I know I was wondering, like, I don't even know if we figured out how we're going to actually get there and travel there or land and then come back and all of that stuff. There are some definitely technological challenges still ahead. But the fun part, like you mentioned, Lindy, of like, we just got to ask what we want to know. We don't have to figure out how we're going to get there.
Yeah.
That is fun part.
I think they're both fun, I would say. And Dave, I know you and your whole community have been working on this forever. So very exciting.
So then what are those high priority science objectives that the report outlines? You know, when I was kind of looking at them, they kind of seemed to, you had several cross-cutting themes and things like, you know, resources, life, husbandry. I called it husbandry. I don't know if that's appropriate or not, but that's what I called it in my mind. So yeah, can you talk to us about what some of those high priority science questions are?
Yeah, so we asked our disciplinary panels of experts, and we combed through four panels of experts in different disciplines, and we combed through over 400 publicly available, published, peer-reviewed documents of people's ideas about what we should be doing. And we put them all together into gigantic lists of hundreds of potential science objectives. And then we had this job on the steering committee to decide which are the most important and how do we rephrase them. And are there topics that have fallen between disciplines that we need to raise to the top? What are the things that maybe are not top priority across all the panels, but when you look, they're in all the panels. And so then they rise up to be more important. And one of the ways we thought about this, because we thought about it many different ways on our way to decision, is we thought about it in terms of cross-cutting themes. And there were 5 of them. Life, past, and present. This is, I mean, what human hasn't asked, are we alone? This is millennial old question. Habitability, the potential for a place to be habitable. And then climate, weather, processes, and history on Mars. So critical, not just for understanding how planets work, but how humans are going to survive on the planet. And then the next theme was human experience and habitation, the science of humans on Mars. And then enabling future missions, questions like in situ resource utilization. So this was one of the ways that we divided up our questions, trying to get away from the disciplinary and toward the topical. We ended up with 11 science objectives in priority order. And I hope that this intro I've just given helps people understand that this is not like number 1 is super important and number 11 is disposable. These are the 11 most important science questions out of the hundreds and hundreds that we considered. So they are all super important, but in priority order, we do start with life. Determine if in the exploration zone, evidence can be found for any of the following: habitability, indigenous extant or extinct life, and or indigenous prebiotic chemistry. You know, are we alone? Was there life in the past? Is there possibility of life? That's where we start, but we really go through 10 more science priorities that do lie across all of those cross-cutting themes that I mentioned, and especially astronaut, you know, the science of humans on Mars. That's how I would start, just for an introduction to the science that we discussed.
Yeah, I like that, the idea of life, you know, starting with the most fundamental, are we alone? But then also like us living on the actual surface as well. That element of life those are both fundamental science questions.
Absolutely.
I'll chime in too, because it's again, there's so much to talk about the science, and for all of us engineers, educating us deeply into the science was again just a super educational, wonderful work. And with that goal is, how can we do science-driven exploration? So I learned a lot about geology and our their priorities, you know, the geological record, the potential niches. I mean, Mars is so exciting. Look at those volcanoes, and we think the you know, caves and maybe lava tubes and all these things that we get to explore. Those are, you know, but and then again, the drilling deep. So it's really exciting to have our Lindy mentioned our wonderful panels of all the experts coming together, and you know, they want to do hundreds and hundreds of geologic, but that's fundamental. What's the geologic record? Right? We need to go to all these very, you know, interesting places as well, or put it this way, and to go on Mars that has these interesting places for us to really do the best science, and the potential niches, of course, back to, are they habitable? Can we find life? But and this integrated, pretty much all the human priorities for science objectives. We call it, the integrated Martian environment. That's a mouthful, but what that means is, again, we have to look at systems, the human body and the astronauts as a whole. That's physical performance, right? We have the cognitive and the mental well-being, keeping people safe. So we talk about that as this, kind of this integrated Martian environment on the emotional, the physical, the well-being of the astronauts. These astronauts are scientists. It's not two different sets of people. They are the scientists, astronauts. And so kind of went through those priorities as well.
We want to go on and talk a little bit more about a few of our science objectives of the 11. We won't be marching through all 11, buy the book. It's out there for free for you to read on PDF. And but especially to talk about question number 3, characterize and map the geologic record and potential niche habitats. To understand the geological context. This one might not be so self-evident about how important it is, but for us to understand everything we possibly can about the kinds of rocks that are in the area around the landing zone, what their histories have been, what they're made of, whether there are health impacts from them, what kind of sand or regolith or soil is created from them. It's a really fundamental question. What is our environment? It's needed both to understand the samples that we take, also understand the history of volatiles like water on the surface of Mars, super critical for human futures, and to also give us context to the other parts of the planet. So that, and then another one that connects to it, I think, in a way that is often passed over, maybe, is to characterize the radiation environment. People do talk about the importance of radiation safety in flight. And maybe it's a little bit not understood how important radiation safety is on the surface of the planet as well. People tend to think about radiation safety in terms of solar wind and solar radiation, but that is not our biggest problem. Our biggest problem is what are called galactic cosmic rays. These little particles that are not just protons or electrons for you cognoscenti, but also can be the nuclei of atoms as heavy as iron. And they carry energy that can be 1,000,000 times more energetic than the most energetic particle we can create in the Large Hadron Collider. And so what happens when they hit the surface of a planet with less atmosphere, like Mars has less atmosphere, is they actually cause the atoms that they hit on the surface to create secondary radiation. So that's a kind of thing that you can't know before you're there on the surface measuring it. And so the importance of understanding radiation at key locations in the crew habitat and all around the area and in the places where we're taking samples, that's incredibly important. And it rose right up to our top 11 as well.
There were also kind of 4 scenarios or campaigns that were laid out in terms of not necessarily choosing the landing site, but kind of thinking through getting there and what it might look like to land. So just give us those scenarios. And actually, I would be interested, what do you think is most likely, or what does the report think is most likely? And do you have a favorite?
Well, let me start with this one. So these campaigns are really important. So what we looked at, we came up with and we prioritized 4 campaigns. So what's a campaign? It's made up of 3 missions. The first 3 missions, that was our remit in our statement of task. So we have priority campaigns. I'll describe a high level for you. And the first, either they're made up of longer or shorter campaigns. What do I mean by that? Okay, a sol is a day on Mars. So imagine a human mission that's 30 sol. And then the second mission that is basically called a cargo mission. Get that infrastructure there. We have to land all this stuff. And then a very wonderfully long scientific mission, 300 to 500 sols. That's one type of a campaign. 30 cargo, 300 plus, we call that. Or another alternative is shorter missions, 30 days, a second mission, 30 days, another mission, 30 days. So that could be a campaign made up of 3 30 sol missions. Okay, now then in priority order are 4 campaigns that kind of have those building blocks, if you will. The very first one is 30 cargo and 300. And we actually have a wonderful name for this. It was Mars Science Across an Expanded Exploration Zone. We're going to like a place 100 kilometers. Our rovers can't do that. So we're going to a very large exploration zone. Why? This is our top ranked campaign from the steering committee because we can get the best science payoff permission. So an initial mission of 30 days, you land, check things out, do some science as much as you can in that kind of month long. Then you need a whole bunch of cargo. And then guess what? When we go back for 300 days, you got to really have that landing site strategically selected. But we can do, we think, all of our 11 science objectives. That's why all of our 11 science objectives, really important. So that's this notion of an expanded exploration zone. The second campaign, and that's a longer campaign, 30 cargo 30. And we love it, the synergy of Mars science measurements. So just think about that. Just think about our 11 top science objectives. What can we get done? Now we can share measurements across life, the water, the geology, all of the resources. And I'd like to tell people, kind of build a 4-dimensional view of Mars, right? You're on the surface, but we're not just on the surface. We're drilling deep, right? Evidence that's what we need to do to find the evidence of life. And we're going up into the sky, if you will, to the atmosphere. So this, these science measurements, really focusing on our science measurements, kind of maximizes the science per measurement. That's how we think about that. It's flexible, doesn't dictate where you need to go. We're just saying, let's be able to do our top science objectives and priorities. The third rank campaign, this one's pretty focused on seeking life beneath the Mars icy surface, icy crust. So go to the surface, and now we need a real push in deep drilling technology because we were talking deep drilling is defined. We defined it in the report as 2 to 5 kilometers.
Wow.
That's
Wow.
deep. We can do up to a meter today. We need to go tens of meters in drilling. And this one's saying, okay, kilometers, because then we can access samples that are in the lower boundary of the Mars, the cryosphere, and that's the top priority for this type of campaign. It's a 30-day, get your cargo, land all your infrastructure, then you do that long stay. It has the highest potential of detecting life, we think, and it's going to advance a lot of the drilling technologies as well. So that was the third campaign we came up with. And the fourth, last one I'll talk about, is this is just 30, 30, 30. So let's investigate Mars for shorter stays, 30 souls each. Maybe we can go to 3 different really wonderful places on Mars and capture the diversity, again, of the geology, of the climate, the timeline. How much science can we do across these 3 shorter stays? It's less risk for the astronauts, these shorter missions, but it's a breadth of science. We'll do a breadth. It's not going to be a depth. We're not there, probably long enough to get too much done, not to do all of our measurements, and it doesn't address all of our top science objectives in this 30 soul mission. But still do. So those are notional campaigns and different things that we wrote about and described to NASA and are talking to folks about. Well, it's pretty exciting. I'd love to do any of them.
Yeah, and one of the things that the report really highlighted was, besides the maximizing time, time that humans were performing science, it was about, all the collections and the samplings and all the science and the measurements. It had to get back. Like you have to keep bringing it back. Every time you go, you have to bring stuff back. So, but yeah, we've got about 5 minutes left. And I wanted to kind of skip ahead a little bit in my questions. Lindy, you had talked about the importance of robotics and what the report dubs as human agent teaming, and that kind of speaks to me about workforce development. I'm thinking, are we even are we preparing enough for that in our workforce for the future of that? But I'm going to morph that question into another question about just broader national policy goals. So how, and you can feel free to pull workforce into this question, but we talked about going, the moon, low Earth orbit, the moon, Mars, beyond, and those are the stepping stones. What, right now, the United States has announced going to the moon, putting, boots on the ground again, having humans there again by 2028, and then having more of a kind of permanent presence or settlement there by 2030. There seems to be a refocus on this, trying to get us up there and building out a cislunar space economy, right? That space in there, and actually having industry be part of that. How does that fit into the national goals for the United States in terms of what are we going to learn on the moon that can get us to Mars? How are we developing the workforce today with lunar science and space science, and then getting us to Mars? So I'm going to kind of make that a big, broad question. But yeah, I invite either one of you to start off that.
Let me just say a short thing first and hand it over to Dava, because I think she's particularly articulate on this topic. I think the thing to remember, we are just talking about science, and we don't want people to mistake the fact that everything we do when we talk about moon to Mars affects every aspect of American society and internationally. It affects the whole world. It's everything from the incredible inspiration of seeing what humans can do when we work together toward a goal that we can define. It's a miracle what we can do in space, and we can do that here on Earth too. So there's the inspiration of that. There's the sense of national pride. Look what America can do. And then there's every kind of stimulus that it does, helping to heal our stressed supply chain in the United States, and everything having to do with workforce development. Watching the students flock to these programs because they are inspired, because they see this is the way that humans can work together. It's incredibly powerful. It brings students into every aspect of STEM fields and everything that we need for the future of our country and really for humans. That's my overview. Dava, take it away.
Yeah, so such a great question. It's like a little bit bigger picture that our report doesn't address, but this is our careers as well. And
Right.
I mentioned that we've been in space on International Space Station for 25 years. Just each mission, each astronaut does 250 scientific experiments. It's amazing. So we're doing so much. So it starts there. Space exploration is about science and all the different science we can do. So yes, we're going to the moon. We're going to the moon with humans. This amazing amount of science we can do on the moon, and the technology development. I do believe it is a stepping stone for Mars. But let's do it internationally. Let's do it globally. Just take a pause there. I think the International Space Station has given us a phenomenal model. 5 major partners. And guess what? Over 100 countries have sent science up to ISS, setting the standards, national leadership, international leadership, soft diplomacy. Soft diplomacy. I want to reiterate that. We can work together. Scientists and engineers, we like each other. We want to get stuff done. Like, let us do the work. And we love working with, again, internationally, across the US. So I think that that's really important. I think we have some great model, and can we play that forward? On the moon, can we do global lunar exploration and the moon village? I actually love that idea. Yes, it's for everyone. We're telling our students, Lindy and I do this every day, telling our students that space is for you, science is for you, engineering is for you, exploration is for you, and go full circle, taking care of our home planet. All of our solar system exploration teaches us, hopefully, about humanity, who we are, what we do best, but let's take care of Spaceship Earth as well. So the international partnerships, the partnerships with industry, the public-private partnerships, we've established that. Now it's a decade old. It's a model. It's a model for the US government. I think it's going pretty well. Really working closely with government funding, the private folks investing, the private folks really putting skin in the game, investing, accelerating the innovation cycles. Space is hard, really, it accelerates, and lots of the good brains too, from academia, from FFRDC, sitting at aerospace doing that. So it just takes this teaming, and so I can't also emphasize how important our public-private partnerships are when we get it right. We're on that path.
Yeah, I appreciate that. The idea of the inspiration that ISS has brought in terms of international cooperation, and yeah, the inspiration and cooperation that people are feeling with Mars as well. And yeah, it's very exciting. Well, I want to thank you guys very much for joining the show today. I really enjoyed talking. I'm excited. I hope that people read the report. You can find it at the National Academy of Sciences website. It's called A Science Strategy for the Human Exploration of Mars. I read the exact title for people. So thank you guys very much for joining.
Thank you so much.
To our audience, you can follow us or subscribe at csps.aerospace.org. All of our shows are available by podcast or on YouTube. And a big welcome and thank you to Matthew Ricola, our newest team member as technical director. And everyone, until next time, bye.